Yes, where is the center of mass if you're talking about the rigid body, which is, if you think about it, almost infinite collection of particles crammed into one region in the space? Are we really going to add up all the masses, all the locations, do the average, the weighted average, so on and so forth? No. We're going to use intuition first and then calculus. That's why right here, rigid body, continuous distribution of matter over space, where distance in all the parts of the body is fixed. Yeah, that's where the rigid part comes in. Oh, thing like that. What's that? Fixed. Yeah, if you consider 2 points on this object here, I don't know, one at the top, one at the bottom, they're at a certain distance. If I throw it in the air, the distance between the 2 points is going to remain the same. It's rigid. In fact, that one is not rigid, right? Because I can change the distance, because it can deform, can bend. So that's a soft solid. Take that table. If I throw the table, don't go in deform. Okay? So in this course, we're only interested in rigid bodies. That's all right. And also, we're going to make simplifications. As an introduction, we're going to assume that the density, the mass density, is the same everywhere in the body. And that's the start. You could then think of composite body, where one part is denser than another, and so on and so forth. For this course, we're only going to take the mass density. I'm going to call it rho. Do you know that letter? That's a Greek letter. The capital is P. Well, it reads like P, but it's rho. There's no clue about the movie. Rogue One! Very good. Well, why is the 2? That's the 1. The Rogue. Big Star Wars! Okay. Wasn't that hard. So rho is the mass density, is the mass divided by the volume if it's a 3D object. But sometimes we're just going to look at 2D objects. So then it's the mass divided by the area. Yeah, I should write what that is. Volume, area for 2-dimensional bodies. And then for 1-dimensional bodies, it's mass divided by the length. And then since the mass density is constant, the mass is uniform, distributed uniformly throughout the body. If I take a part of if I cut it in half, then it will be the mass of that half divided by the volume of that half, and so on and so forth. Any subset of that body will have the same mass density. Okay, so we keep that in mind, and then we start using our intuition to figure out where the center of mass is. Remember, it's a weighted average according to the masses, but if the mass of each particle of each sub area is, if each sub volume of the body has the same mass density, then it's going to be the same everywhere. It's going to be okay. We could just figure it out. Yeah, if I had this symmetry, for instance, if I have a disk like this, very thin disk, or even thicker, I can see from symmetry considerations that the center of mass is going to be just there, at the middle, at the center of the disk. Yeah? Makes sense. Similarly for a sphere, if I have a sphere, clearly the center of mass is going to be at the center of the sphere. If I have a half sphere, then it's not so obvious. Where is it going to be? Halfway up? I don't know. We'll have to do calculation. For full sphere, by symmetry, you can guess that's where it's going to be. Similarly, if you have a rod, say something like this, of uniform density, it's going to be exactly in the middle here. If you have a square, if you have a rectangle, you're going to have symmetry here, axis of symmetry here, another one here. So since the center of mass has to be on the axis of symmetries, on both, it's going to be at the intersection of those two axes, and so on and so forth. The more symmetry there is, the easier it is. What about a triangle? What if I had a triangle of any length on the side? How am I going to find the center of mass? What I do, okay, yeah, is that I'm going to divide, okay, I'm going to divide the triangle into thin strips. Say I start from this end, from this edge here, going to divide it up into thin strips, add them all up. I know that for each strip, the center of mass is at the middle here, here, and so on and so forth. Here, that's going to be center of mass. By symmetry, I know it's at the middle there. Center of mass of the other strip is going to be in the middle of that other strip. I add all the strips together. I know that the center of mass now is going to be the center of mass of all those centers of mass. So it's going to be somewhere on that line here, which is the median. And let's call it X. It goes through the center of mass every strip. So I know that the center of mass of the triangle is on X. That's one thing. But then I just chose that edge to divide the triangle into strips. I could have chosen that edge here and divided into little strips that are parallel to that edge. Or I could have done parallel to this edge here. I could have that is really ugly. Just gonna redo it. And I would have found that with the same reasoning, that the center of mass of the triangle should also be on Y, say, and then it should also be on Z, say, the median, the other median. it's also other medians. Conclusion must be, but that didn't work out too well. Must be at the intersection of those three medians. Okay. How do I do that? We have to delete this one. Okay, well, I hope you're better than me at drawing. Well, if you take three medians, they meet in the middle, in the what's called the centroid of the triangle. Why can't I delete it? Okay. Sorry, I'm limited. I don't know how to fix that. This here. Oh. Oh. Okay. I can't erase. Turns out I can't erase my lines. So hopefully you have it better than me. You know that the medians of a triangle meet in the centroid. And so for a triangle, the center of mass is the centroid, which is why I've written that on top here. We show that the center of mass lies at the centroid. So we only did this through reasoning here. We just used our intuition. We did do something clever, which was to divide the whole object into smaller objects for which we knew where the center of mass was. 5, 7, 9, 12, 21, 22, 13, 14, 16, 18, 19, 20. Poker face. Anyway, so yeah, the clever bit was to divide the object into smaller subsets for which we knew where the center of mass was. And then you average those center of masses to get the final center of mass. So here there's no calculation, just reasoning, but now we're going to do some calculations. So what if we have a half sphere, or in this first example it's a half shell, right? So that's a 2D object, it's hollow, and we want to find where the center of mass is. So there's one axis of symmetry, is the x here. You see, that's a symmetry for this hemispherical shell. So you know center of mass is going to be somewhere on x, but that's where the symmetry ends, right? The vertical axis is not an axis of symmetry anymore. What can we do? Well, we can do the same as we just did, is divide the object into smaller objects for which we know where the center of mass is. If I was to slice my sphere, my spherical shell, into thin strips, each strip would be like a thin circle, right? A circle with a small width. And I know for each of those circles that the center of mass is the center of that circle. But the center of mass of this strip here, I hope you can figure it out from the drawing. Yeah, you see how it goes? Goes around like this. I know the center of mass is just there for that strip at that point here. So I'm going to call those rings. So I blew up the scale, but you have to think of it as really, really thin. That's why I call this angle delta theta. The idea is that it's very small. So let's look at that ring here. I know where the center of mass. So A is the radius of the sphere, or the hemisphere. So that distance here, where the center of mass is for the ring, got a new pointer. Fair. That distance here, that's the horizontal distance. In that triangle, I can see that A is the hypotenuse. Okay, let's just draw that triangle on the side. It's like this. So I call theta the angle. A the long side. If I call B and C, I can see that cos theta is C over A. Sine theta is B over A. So that tells that's why it's written A cos theta here. Right? C is A cos theta. So that's the position of the center of mass of the ring on the x-axis. Okay. So that's good. Now I can go through this reasoning I've made here. Divide the hemisphere into rings of radius. Oh yeah, what about the radius of the ring? It's going to be this height here. It's going to be what I call B. B is A sine theta, which is why I've written A sine theta here for this height. And so the radius of the ring is A sine theta. That's correct. The width is going to be this length here. That's the arc length. If A is the radius and delta theta is the angle, this arc length is going to be A delta theta. So that's all correct. The center of mass, like I just said, is located at this distance, A cos theta, from the center of the hemisphere. Okay, so now we're going to bring in the mass density. So first we need to compute the area of each ring. Going to call it delta A. Area of each ring. So a ring is going to be the perimeter of the ring multiplied by the width of the ring. So the perimeter, that's 2 pi r. So in this case, it's going to be 2 pi, and the radius is A sine theta, times the width, A delta theta. Perimeter okay. I'll just go slowly. The density, that's the mass divided by the area, because this is a 2D object. What's the area of a hemisphere? Surface area of a sphere is, that's in the book, a sphere is, remember? It's in early pages of the book. So it's going to be 4 pi r, well, in this case it's A squared. Yeah. It's on page, the first, no, third page, page number 10. 4 pi r squared, where r is the radius. So in this case, it's A. So if that's surface area of a total sphere, a hemisphere, half a sphere, is going to be 2 pi A squared. Okay. So that's for the total hemisphere, but it's also true for each of those rings. Right? It's going to be delta M over delta A, where delta M is the mass of the ring. So from this equation I've just written here, I can find delta M. Delta M is going to be rho delta A. So that's going to be M by A squared. Delta A, I have it above, 2A A squared. Yeah, I just regrouped the A's here. A times A, that's A squared, 2 pi sine theta, yeah, and then that's rho. These two terms cancel out, so it's actually pretty simple. I'm just left with m delta theta. Well, that's clever. So now I know the position of the center of mass of each ring. And I can just do the summation for each ring. I can do the formula for the center of mass. I know the center of mass is 1 over m, sum of the m minus r, but in this case, it's not particles, it's rings. But I can still write the formula. It's going to be 1 over m sum over all the rings of delta m times x, which, like I just saw, is m sine theta delta theta, and x is the position of the center of mass of each ring, which is a cos theta. So simplifications ensue. I'm left with a sum over all the rings sine theta cos theta delta theta. Okay. So now I have to sum that. That's not obvious either. How am I going to do this? I have to look at this as a sum of each of those terms. If I look at those terms as height multiplied by width, yes, that's clever. Look here. I'm going to look, see the sum and approximation to the area under the y equals sine theta cos theta curve. I'll show you how you can see that. Right here, I'm just going to plot y, which is sine theta cos theta. It's a function that goes like this from 0 pi over 2. Yeah, I forgot to specify here theta is between 0 and pi over 2. Yeah. When theta is 0, I'm here, and then as theta increases, I go all the way to pi over 2. So that's my function y. If I look at this quantity here, sine theta cos theta times delta theta, it's going to be, say, this point on the curve, sine theta cos theta. And if I multiply by delta theta, I get the area of this small rectangle. So here I'm summing all those small rectangles. As theta changes, the rectangles are going to follow the curve. They all be of width delta theta. And I can see that this is true, right? This sum of all those small rectangles is going to be close to the area underneath this curve, right? There's a little triangle missing here, but it's going to be close enough. It's an approximation. And in fact, if I reduce the width of delta theta, if I take it smaller and smaller, the area missing, the little triangle, is going to become more and more negligible. Ah, that's so clever. As delta theta tends to 0, my sum is going to tend to what? So this is an approximation of the area underneath. What's missing is that little triangle, right? If I want to compute the area underneath, I should go all the way there. But if I reduce delta theta, that triangle is going to be smaller and smaller. And so that area is going to tend to the sum of all those rectangles. It's going to tend to what? How do you compute areas in general underneath the curve? Yeah, it's the integral, right? It's going to tend to this. Do you believe me? Do you see it? That's so smart. Okay, I'll show you again. If I was to sum up, like I'm doing here, all those little rectangles, I will get an approximation to the area underneath the curve. I'll just be missing the area of those small triangles. So I'll be close enough, but not exactly computing the area. That's why I say approximation. But if I take delta theta to go to 0, then the area of this small triangle is also going to tend to 0, and so my sum is going to tend to exactly the area underneath the curve, which is the integral. How can you do that? No. No. Okay. Oh yeah. And now I know how to compute this here in the limit xcm. How do I compute this? Sin theta cos theta. If I look in the book on page 24, I can see that 2 sine A cos A is sine 2A. So here really I have 1/2 sine 2A, or 2 theta in this case. And I know how to compute this integral now. Is going to be A over 2. What's the function that gives me a sine as a derivative? It's the minus cos. All right. And then I have 2, so I must put a half to compensate. Yeah. If I was to differentiate minus cos, I'll get sine. If I was to differentiate cos 2 theta, I'll have to bring the 2 out. So I'm cancelling out with my 1/2. So I get minus A over 4. And then I need to evaluate cos 2 theta at pi over 2. That's going to be cos pi. And then at 0, what's cos pi? That's on page 13. It's minus 1. What's cos 0 is 1. So I get A over 2. Huh! All of that just to find out it's exactly in the middle of the half space. Now we know. Not easy, eh? It's midway between the base of the hemisphere and the summit of the hemisphere. It's just there in the middle. That's where it's... I don't know. I don't think it's intuitive. Like, if you think of the vertical axis passing through, it's not an axis of symmetry. It wasn't obvious. What if the hemisphere is solid now? If instead of half ping pong ball, I have now a half golf ball. How am I going to do that? So here, that's a 3D body now. So it's much is much of the same thing, but instead of areas, we have to deal with volumes. Right? If I look in the logbook, I see that the volume of a sphere is 4/3 of pi r cubed, well, here it's a. So the volume of the hemisphere is going to be 2/3 of pi a cubed. I'm just going to do the same reasoning as I did earlier, but now it's 3D instead of 2D. It's solid instead of a shell. So by symmetry, I know it's going to be somewhere on the x-axis. That's the only axis of symmetry I can think of. I'm going to divide it into, instead of rings now, it's going to be disks, solid disks. All right, this is full. And then, what did I write? The width is delta x. Right, so I know that for each solid disk, the center of mass of each disk is here at the center of the disk. I'm going to call x its position. And so if I look at this triangle here, this right angle triangle, if that's x and that's a, that's going to be square root of a squared by Pythagoras. Right, that's going to be the radius of the disk, which is what I wrote here. Radius is a squared minus square root of a squared minus x squared. So we do the same reasoning now. Volume of each ring, volume, and so on and so forth. Introduce density, and then find the mass of each ring. So volume of each ring, delta V, is going to be pi r squared. How did I do that? So now I have a disk of radius r, which is square root r, and thickness delta x. Thickness of the disk. So the volume is the area of the disk pi r squared times its thickness delta x. So that's going to be pi a squared plus x squared delta x. The density, I can do the density of the whole hemisphere. It's going to be m over its volume, which is now going to be 2/3 of pi a cubed. Yeah, just take half of what I have on top there. So that's 3m over 2 pi a cubed. But since it's uniform, I can also say that it's the mass of a disk divided by the volume of a disk. The volume of a disk I have it above. The mass of a disk, I'm going to find it now from this equation. Oh, I shouldn't say ring, I should say disk. Is going to be rho delta V. I get it from this equality, rho to delta V. And rho I have it here is 3m over 2 pi a cubed. And delta V I have it above pi x squared delta x. So the pi's cancel out. Okay. And now I know center of mass of each disk. I can write my formula for center of mass in general. I know that it's going to be like this. The weighted average of the position of each center of mass. Each center of mass for each ring is located at x. Each disk, has mass delta m. That's the total mass. I just write that now. It's going to be 1 over m sum over the disks delta m, I have it above, x squared minus x squared times x, times delta x times x. So there's a few simplifications. What are they? The m's come out. 3 over 2a cubed, that's just a constant. And then I'm summing. So I'm multiplying by x, so it's going to be a squared x minus x cubed delta x. And now I can do the same reasoning. I can say this here is the sum of all the little rectangles underneath this function here. If I take delta x to go to 0, this is going to tend to the integral of this function here. Take delta x goes to 0, and then you find that this is going to turn, what's x going from 0 to a? It's going to turn into an integral. And now I know how to compute this integral. I can find the answer. Is it going to be a over 2 again? I don't know. Okay, 6 minutes. We could take our time. So a squared, that's just a constant. What's the integral of x? X squared over 2. Yeah. If I differentiate x squared, I got a 2 coming in front. I won't get rid of it, so I put 1, 2. I got x. What's the integral of x cubed? x4, right? 1/4. Now I evaluate this at a, and then at 0 it's going to be 0, so that's easy. A squared times a squared over 2 minus x4 over 4, and then minus 0. I don't need to write it. 4 over 4. What's that? That's going to be a4 over 4. And so I found that the center of mass for a solid hemisphere is at 3/8 of a. So nothing obvious there. No way you could have guessed that. And different from the shell. So these are tricky exercises. The reasoning is okay, right? You use symmetry as much as you can. When you count them out, then you divide it into sub-elements for which you know where the center of mass is. And then you have to do all this machinery. Not easy. But you expected to know those two at least. Hemispherical shell, hemisphere. Hey, question. That was hard. No jokes. Maths movie quiz in the beginning. It was all downhill after that. You can donate a joke, yes. Anybody else's jokes?
Well, I mean, I have an entitled joke.
Go on. Can you give it to me? Now? Later?
I don't have it now.
Oh, okay, okay. Anybody has a joke there? No? Tomorrow.